In today's segment, we'll discuss about important topic from DSP. It is digital filter structures. Now, in this segment, first we'll discuss about what is meant by filter. Then we'll discuss about classification of filters, and then we'll come across realization structures of digital filters. Now, first, we all know that filter is an electronic device which is used to remove unwanted signals or noise. Now, as far as the classification is concerned, so the very first type of filters is known as analog filter. Now, these analog filters are made up of components like R, L, C. It is resistor, inductor, and capacitors. Now, coming to the part of how actually digital filters. So basically, digital filters are made up of components like multipliers, adders, and delay elements. So by the combination of all this, digital filters can be formed. Now basically, there are few types of digital filters that we'll discuss, and then we'll switch to its realization structures. Now there are two types of digital filters. The very first is known as finite impulse response filter, which is abbreviated as FIR filter. It is a filter whose output depends upon present input and previous input samples only. For example, if I consider I'm having an input as x of n and output y of n, then here output depends on the present input terms as x of n with previous input samples as xn minus 1. And in this case, the impulse response, generally denoted as h of n, is finite. So it may have values as 1, 2, 3 and 4, which are going to be finite. Now coming to the part of second type, it is known as infinite impulse response filter, which is also known as IIR filter. So it is a filter whose present output depends upon present input samples, previous input samples and output samples. That means, as far as the system is concerned, here the present output depends upon present input, let xn, previous input xn minus 1 and output samples as yn minus 1. Now in this case, the impulse response is infinite. So you can see we are having samples like 1, 2, 3, 4 and so on. So these are the two types of filters that we need to discuss and that we need to realize it in terms of the structures. Now basically, digital filter is nothing but an LTI system, that stands for linear time invariant system, which has three terms: xn as an input signal, y of n output, and h of n simply indicates response of the system. And in order to realize this system, either you can find h of n or we can find h of z by solving difference equation that relates x of n with y of n. And there are so many ways by which you can solve these difference equations, and that process is known as realization structures of filters. Now in first segment, we'll discuss about. Now let us start with direct form 1 realization of IIR filter. As we have seen that IIR filter is one in which output depends on present input with previous input samples and output samples. So let us consider that we are having an LTI system with the difference equation like this. Now we'll simplify this equation. So you can write this as y of n is equals to, first value I am considering k1, we'll get a1 as the coefficient, yn minus 1 minus next value as 2, a2, yn minus 2, and the last value I am writing, that is minus an yn minus n, plus next we'll simplify for this equation also, starting with 0 to m. We'll get the first coefficient as b0 xn plus b1 xn minus 1 plus b2 xn minus 2, and the last value I am considering as m, so it is bm x minus m. Now in order to realize this difference equation, first I am assuming that these input terms with another variable as wn. So let us assume that wn is equal to all input terms I'm writing b naught xn plus b1 xn minus 1 b2 plus bm xn minus m. Let us assume that this is our first equation. Now if it is wn, we'll rearrange this equation and we'll get the output equation as yn is equals to a1 yn minus 1 minus a2 yn minus 2 minus an yn minus n plus this term as wn. Let this is my second equation. Now we'll realize these two equations and that becomes our direct form on realization. Now as far as realizing equations is considered, we need several elements like adders, then we need some multipliers as well as some delay elements, maybe x of n minus 2, x of n minus 1, x of n minus m. So all digital filters can be formed by using three elements: multipliers, adders and delay elements. Now first we'll realize equation number 1 and then we'll realize equation number 2. As far as this equation is considered, so if you observe, x of n is input and w of n is output. So I'm writing this term. This side I am writing input as x of n and here we'll assume that output is wn. As far as this equation is considered, wn is equal to, first term it is b naught into xn. So we need one multiplier. So we'll take one multiplier. The coefficient is b naught. So wn becomes b naught into xn plus next term is x of n minus 1. So in order to generate x of n minus 1, we'll use one delay element as z inverse, whose input is xn and output becomes x of n minus 1. Now it is multiplied with b1. So this is b1. Similarly next xn minus 2. So another delay element will add as z inverse. Now the input of this term is x of n minus 1 and its output will be x n minus 2. Now it is multiplied with b2. It's multiplied with b2. Next to the last term we'll take. So I'm writing it here. So on. Another delay element z inverse is multiplied with bm. Now these all coefficients are added. So we'll add, this is a plus, plus and plus. So on. The last element will be added in the same way. So here all these terms are added. And based on that we'll get the output as wn. Now if you observe it carefully, wn is addition of b naught with xn, b1 with xn minus 1, b2 with xn minus 2, so on up to bm into xn minus m. So this is a realization of equation number 1. Now the same concept we will adapt for equation number 2. Now if you see equation number 2 here, your output is y of n and the input terms are wn with output samples yn minus 2, yn minus 2 and so on. So in order to realize this, again if you see y of n, if I rearrange this equation in a proper way, we can write the same equation. Yn is equal to wn is added with terms like a1 minus a2 minus an yn minus n. Now we'll realize this equation. So again, this is input, this is output. So this becomes input and here I will add that output term. Let it is yn. So first, y of n is equals to wn. So we'll extend the same line over here. This is y of n is equals to wn. Now if you see, we need y of n minus 1, n minus 2, n minus n. That means delay elements are introduced. So here we'll introduce first delay element, z inverse. Now here the input is y of n, so its output will be y n minus 1. And it is multiplied with the coefficient as minus a1. So it is multiplied with minus a1. Similarly next, y n minus 2. We'll add one more delay element, z inverse. Now here the input is y n minus 1, output is y n minus 2 multiplied with minus a2. Similar to the last term, as z inverse with a term as minus a n. Again all these terms are added, so we'll use adders plus plus plus, so last term will be added in the same fashion. So this is added, and finally we'll get the term as y of n, and this becomes direct form 1 realization of IIR filter. So it is basically a combination of all zero system with all pole system, only intermediate term added as Wn. So as far as this schematic is concerned, we need adders, elements like adders, we need multipliers, and we need delay elements. So by this method one can realize an IIR filter which is direct form 1 realization. Now in the next segment we'll see some of the examples on realizing IIR filters using direct form. Let us consider the first example on this. Obtain direct form 1 realization for the system given below. Now here it is a difference equation with the terms like y of n, n minus 1, n minus 2, and x of n minus 1, x of n minus 2. Now the process is simple. First we'll go with the traditional method. Let Wn is equal to all input terms x of n, x of n minus 1, n minus 2. So just consider this is equation number 1. So we'll get the output term yn as 2yn minus 1 plus 3yn minus 2 plus wn. This is my second equation. Now we'll realize equation number 1 and 2 with a similar fashion. As far as equation number 1 is considered, again xn is input, wn is output. So remember every time to the left we'll write the input terms, and here we'll write the output terms. So x of n with wn. First wn is equals to xn, so we'll extend the same line, and it is multiplied with let 1 because here the coefficient is 1. Next we need xn minus 1, so we'll add delay element from here only. This is z inverse. Now the output of delay element becomes xn minus 1. Now this xn minus 1 is multiplied with 2, so this coefficient is 2. Next we need xn minus 2, so here we are getting the input as x of n minus 1. We'll apply the same input to another delay element as z inverse. So it will delay this input signal by 1 unit, whose corresponding output becomes xn minus 2 with the coefficient as 3. So it is multiplied with 3. Now as far as this equation number 1 is considered, we need two adders. You can see this is first and this is second adder. So here we'll put those adder terms, first and second, and these all terms will add. So these are added, and here we'll get wn. Now we'll realize equation number 2 in the similar fashion. Now here y of n is output, wn is input, and these are your output samples. So first y of n is equals to wn. This line will extend in the similar fashion. So again this becomes our output, this is our input. Next we need yn minus 1, n minus 2. That means here we should add those delay elements. Let this is z inverse. It is multiplied with 2. So this is multiplied with 2. Next yn minus 2. So I will add one more delay element here, whose corresponding output becomes yn minus 2, and it is multiplied with 3. So it is multiplied with 3. Now again for this equation we need two adders. So this is the first adder and this is second adder, and finally we'll add them. So this becomes our output as y of n, and this becomes direct form 1 realization of the difference equation. Let us consider one more example. Now here, instead of wasting too much time on writing w of n and y of n, I am simply consider this is my wn, and that becomes our entire equation. Now we'll realize this. So for this case, again we'll take the same terms. This is input xn, this is output as wn. As far as this equation is concerned, wn is equals to xn. That means we'll take the line same. Next, xn minus 1. So only one delay element is required. This is z inverse, and the coefficient is 0.4. So this is 0.4. Now for this equation, we need only one adder. So we'll take only one adder over here, and this element will be added. So this becomes our wn, and this is my input as xn. Now we'll come across the remaining equation. So you can see y of n is addition of this with wn. So wn will take in the same fashion like this, and let this is my output as yn. Now we need yn minus 1, yn minus 2. So for generating yn minus 1, we'll take first delay element as z inverse, whose corresponding output becomes yn minus 1. Now it is multiplied with plus 0.5. Here it is plus 0.5. Next we need yn minus 2. So we'll use one more delay element whose input is yn minus 1 and output becomes yn minus 2. Now it is multiplied with minus 0.25. So this is multiplied with minus 0.25. As far as this equation is considered, we need two adders only. This is plus and this is plus. So we'll use one adder here, one more adder here, and final element is added in the similar fashion. This becomes y of n, and these terms are added. So this becomes direct form 1 realization of the given difference equation. Thank you.